Okay, should we start?
Sure.
Okay, so second lecture is about eigenvalues and eigenvectors of square matrices. And let me start out reminding you of the classical situation over a field. So let's take a field to be rational functions in one variable t with rational coefficients. And let's take a square matrix. Let's take a 2 by 2 matrix. So for instance, t to the fourth, t to the minus 3, t squared. And so that's a 2 by 2 matrix with entries in a field. So we know how to calculate eigenvalues and eigenvectors. So it has two eigenvalues. Which we can calculate with the classical quadratic formula. So the eigenvalues are square root of 4t plus t squared minus 2t cubed plus t to the fourth, for example, over 2 plus t over 2 plus t over t squared over 2. And then there's a corresponding minus. I'm just going to copy this. Minus 4t plus t squared minus 2t cubed plus t to the fourth over 2 plus t over 2 plus t squared over 2. So those are the two eigenvalues of this matrix and the corresponding eigenvectors. So there are two different one-dimensional eigenspaces. And so this eigenvector is eigenspace is spanned by t to the fourth plus the square root. So this is the same square root as there, minus t over 2 plus t squared over t. And then the second one is t to the fourth minus that's square root over 2 minus t over 2 plus t squared over 2. So that's all very easy. That's how you calculate eigenvalues and eigenvectors for a matrix over a field. But now let's send t to 0. So t plays the role of epsilon. So whenever we relate tropical math with classical math, we have some deformation parameter. So if you like calculus, this parameter is epsilon. That's the same as t. If you like number theory, this parameter is p. If you like physics or combinatorics, it's called q. Okay, so t and q and epsilon and p, they're all the same thing. They're a parameter that's built into the field. So let's use this parameter and see what happens as t goes to 0 from above. Right? So the eigenvalues in this example, the eigenvalues are plus minus the square root of 2. Right? So you can see that the dominant term, so here the eigenvalues, so the dominant term as t goes to 0 is going to be the square root of 2 here, right? And this 4 cancels this 2. In the eigenvectors, are approximately t to the fourth plus minus t to the power a half. Okay, so this was my 4-minute review of classical linear algebra eigenvalues, eigenvectors. So now let's see what we can do in the tropical setting. So now, tropical. Is this large enough? Am I writing large enough?
Sure.
Yeah. Oh, I'm sorry, t squared over 2.
And for the bottom one,
Yes, same thing. That's a typo. Yes. Okay. So of course, to find the eigenvalues and eigenvectors, you might have to go to the algebraic closure, right? So this is just ordinary linear algebra over a field, right? So this is definitely undergraduate mathematics, and this is something you can do. Okay, tropical. So let's say we have an n by n matrix. So let A be an n by n matrix with real entries over the tropical semi-ring. So sometimes I write R bar by taking the real numbers together with plus infinity over the tropical semi-ring. And then by an eigenvalue, of A, I'm going to take to be a real number. I'm going to disallow plus infinity to be an eigenvalue. So an eigenvalue of this matrix is a real number lambda such that A times V equals lambda V for some vector V in R to the n. And such a vector is called an eigenvector. Okay. So I'm allowing the possibility that V is the all zero vector. Remember, 0 is the multiplicatively neutral element. So it's allowed for V to be the all zero vector. But I'm not allowing here in this definition, I'm not allowing any infinity coordinates. Okay, so both lambda and V have real number entries. So these are eigenvalues and eigenvectors. So example, well, let's take this matrix and let's tropicalize the matrix. So we just take the exponents. So 1, 4, minus 3, 2. So those are always the order of vanishing. That's our matrix A. And let's try this vector V, 4 and a half, 0.5, which is suggested, which are the values of the eigenvectors. And then unsurprisingly, you get that this is 0.5 times, I'm sorry, this is 4, this. So I multiply this, and I get 4.5 and 1, which is, of course, 0.5 times the vector I start with. Okay, so this is an example. So here the eigenvalue is a half of this matrix, and the eigenvector, corresponding eigenvector, is 4.51. Okay, and it's the obvious, translation of the classical example on the left-hand side. Okay, now what is the eigenspace? So an important question I like to address. Suppose we have an eigenvector. What is the eigenspace? Okay, so the theme of this lecture and some of the discussions we will have, suppose we have an eigenvalue, AV equals lambda V. What can we say about the set of all V that satisfy this equation for a fixed lambda? Okay, what is the eigenspace? Now in classical mathematics, the eigenspace is a linear space. It's a linear vector subspace of k to the n. But linear spaces are very, very delicate in tropical mathematics. So in lecture 5, we will discuss linear spaces. And one thing to be learned is that the eigenspace is not a linear space. The eigenspace will not be a linear space. But I'm getting ahead of myself. So I'd like to explain to you a little bit more. I'm going to state a theorem. I'm going to prove something. And then I'd like to convince you that eigenspaces are not linear spaces. Okay, let's start with a theorem. So I'm going to write G of A for the directed graph. So the weighted digraph with nodes. So when I write bracket n, I mean the first n positive integers, 1 up to n. that corresponds to the matrix, right? So I have a matrix, and then I have an edge from I to j with weights I to j, and so there's no edge if. So it's possible, that aij is plus infinity, and then there's no edge in the graph. So if the matrix entry is plus infinity, that means there's no flight from that city. There's no direct flight from city I to city j, and then I put plus infinity. Okay, theorem. So here's a theorem. Suppose the graph G of A is strongly connected. So I have the matrix represented as a directed graph with edge weights, and strongly connected means if I have any two cities, I and j, I can fly somehow from I to j. There exists, a sequence of directed paths that takes me from any city to any other city, which is a reasonable assumption in some flight network. You can somehow get from anywhere to anywhere, but you might have to take many steps. So suppose the graph is strongly connected, then the corresponding matrix A. So in particular, if there are no infinity entries, then it's the complete graph, then it's strongly connected. So this assumption says I'm not allowing too many entries that are plus infinity. Okay, so then A has precisely one eigenvalue. It has precisely one eigen. Every n by n matrix has precisely one eigenvalue. It has one eigenvalue. Okay? And I can tell you what this eigenvalue is. This eigenvalue equals, the unique eigenvalue equals the minimal normalized cycle length, a minimal normalized length of a directed cycle, of any directed cycle in the graph. So by this I mean the following. So suppose I have a cycle in the graph. So a cycle is something like this. I1 goes to I2, goes to I3, and somehow in the end, that goes to IM, and then it comes back to I1. So a cycle of length M is, it's a directed cycle. You go from city I1 to I2 to I3 to I4, and you come back to IM. And then the length, the normalized length, is 1 over M, the number of cities in the cycle, and then you add up the prices. So A I1, I2, A I2, I3, plus A IM minus 1, IM, and then to get back, you go IM, I1. Okay, so this number, you look at this number for every directed cycle, and you take the smallest such number for any directed cycle. That's called the minimal normalized length. And normalized is because we're dividing, 1 over m, and this is classical arithmetic. So that's the unique eigenvalue of an m by n matrix. Let's test it for this example. So in this example, for this matrix, a half is a unique eigenvalue. Well, let's draw the graph. So in this case, the graph has only two nodes, 1 and 2. So there's an edge of weight 4 that goes like this. There's an edge minus 3 that goes like this. And then there's a loop like this of weight 2. And then there's a loop of weight 1. So this is the picture for this matrix. And so there's the shortest minimized cycle length. It's this cycle. You go from 1 to 2 and back to 1. That's a cycle of length 1. But its normalized length is a half. And that's smaller than the normalized length of any other cycle in this graph. So the unique eigenvalue of this matrix is a half. Okay, so I'm going to prove this theorem. I'm not going to prove a lot of things in this course, but I'm going to prove this theorem. Okay, so proof. So let lambda of A denote the minimal normalized cycle length in the graph. So that's some number that depends on the matrix, and I'm going to be calling it lambda A. So I have to show you two things. I have to show that this is an eigenvalue, so existence, and I have to show it's the unique eigenvalue. What I'm going to do is I'm going to show uniqueness first, and then I'm going to show existence. Okay, so I'm going to show that any eigenvalue has to be equal to this number. Okay, so let's do uniqueness. Okay, so suppose we have a solution to the equation AZ equals gamma Z. So gamma is some eigenvector, gamma is some eigenvalue, and Z is some eigenvector. So I claim that gamma is equal to lambda A. Okay, so that's the uniqueness part. Well, to show this equation, I'm going to show two parts. I'm going to show that gamma is less or equal, and I'm also going to show that gamma is greater or equal. Okay? So less than or equal, well, for any cycle, let's look at a cycle. So for any cycle in the graph, let's look at a directed cycle. I1, I2, I3 up to IK, I1. We have the following. Well, we have that A, I1, I2, and I'm going to take classical arithmetic, plus Z2, Zi2 is greater or equal to gamma plus Zi1. Why is that? Well, that follows, from this equation, right? Because this number, gamma plus Zi1, that's the I1 coordinate of this vector. But the I1 coordinate is the minimum by, if you read this equation, it's the minimum of these expressions where I2 runs over all indices. So therefore, this is less or equal than any other number, right? So this is equal to the minimum of these, so therefore I have this inequality. Okay, so then by the same token, I have A, I2, I3 plus Z, I3 is greater or equal to gamma plus Z, I2, and so on, right? And so I do this all along the cycle, and at the end, dot, 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 I get A, IM, I1 plus Zi1 greater or equal gamma plus Zim. So I have M inequalities like this. Now I'm going to add the left-hand sides, and I'm going to add the right-hand sides. Well, what happens is that the Z terms cancel out, right? If I add all the left-hand sides, every Z in these inequalities appears exactly once, either on the right-hand side or on the right-hand side. So what I get by adding the left-hand side and right-hand sides, I get that AI1, I2 plus AI2, I3 plus AIM, I1 is greater or equal to gamma, and I think that's a K. I'm sorry, I call this K here. Okay, so it's greater or equal to IK, but this one I have K times, right? Because they're K inequalities like this. So I have this sum is greater or equal to gamma times K, but that's exactly the inequality I want, right? So I found that gamma, so I divide by K, so then I have this inequality, this is greater or equal to gamma, so I've shown that my eigenvalue gamma is less or equal to the normalized cycle length for this particular cycle, but it's an arbitrary cycle, so therefore gamma is less or equal to the minimum over all cycles. Okay, so that gives me this inequality. Okay, so now let's do the reverse inequality. Okay, so I've shown that gamma is less or equal to lambda of A. Now I'm going to show that gamma is greater or equal to lambda of A. Okay, so for that, let's start with some index. I'm going to start with any index I1. Well, then there exists an I2 such that AI1 I2 plus Z I2 is equal to gamma plus Z I1. So I now turn backwards. So, from the point of view of I1, there exists an I2 which attains this with equality, right? Because we have this equation. That's a minimum equation. So for I1, there exists an I2 so that I have equality here, and so on, right? So there exists, then for that I2, there exists an I3 such that, the next one has equality. AI2, I3 plus ZI3 is equal to gamma plus ZI2, and so on, okay? Well, we're going to continue this. Until, but now there's no cycle, right? I'm just starting with any index I1, then I find an I2. Then for the I2, I find an I3. But the graph is finite, right? So eventually, I'm going to come back, and I'm going to continue until, IK is equal to IL for some L less than K, right? So I'm flying, right? I'm taking a trip on Korean Airlines. I fly, from some city. Then I get to a new city. They tell me go to some other city. Then I get there. They tell me go to some other city, right? Eventually, I'm going to come back to a city that I've already been to. It may not be the first city, but some earlier city I'm going to revisit. So eventually, my kth city will be equal to my lth city. Well, then, what I found then, I've produced a cycle. I've flown a cycle. Ik plus 1 IL back to Ik. So forget the initial segment, right? So eventually you're going to revisit a city, right? So eventually you're going to get to Nagoya, right? And then, you come back to Nagoya. Never mind you started in Busan, right? So then you look at this cycle, and then that cycle is a cycle. You've made a cycle of normalized length gamma, right? So I've produced, I made a cycle. I've produced a cycle of normalized length gamma. But, therefore gamma is greater or equal to the shortest normalized cycle length, and that's the correct inequality. So that proves the uniqueness part of this theorem. So I've shown now to you that every n by n matrix has at most one eigenvalue, namely lambda of A. So now I have to show to you that it has at least one eigenvalue. I have to show that lambda of A is actually an eigenvalue. Okay? So that was the uniqueness. Now let's do the existence. The existence part. So how does this go? Well, I'm going to give you an algorithm. So I'm going to give you an algorithm that produces an eigenvector. Okay, so I have to, to show that gamma of A, that lambda of A is an eigenvalue, you have to find at least one eigenvector. So I'm going to make an eigenvector for you now. So here's an algorithm for making an eigenvector. So here's how it goes. You're going to set B to be classical minus of lambda times the matrix A. So you're going to scale the matrix by this constant, minus of lambda A. Right? But that's a scalar multiplied against the matrix, but this is tropical, scalar addition or scalar subtraction. I mean, in concrete terms, what this means, you're subtracting lambda of A from every entry of the matrix to get a new matrix called B. Now what about B? Well, all cycles in the graph of B have non-negative length. Right? So all cycles have non-negative length, and there exists a cycle of length 0. Right? So I've taken the shortest cycle length, I subtracted it. Right? So every cycle in A is a cycle in B and vice versa, but I've just shifted it so that the shortest cycle length is 0. Okay, so now I have to, and the eigenvectors are the same. So the eigenvectors of B with eigenvalue 0 will be the same as the eigenvectors of A with eigenvector lambda. If you scale a matrix by a constant, right, and then the eigenspaces stay the same, just the eigenvector shifts. So I'm going to make an eigenvector now for B. So to do this, we're computing the following matrix. Let's compute the following matrix, which I'll call B star. So B star is B plus B squared plus B cubed plus B to the n. Okay, n is the number of nodes in the graph. Okay, I'm going to call this B star. And I could go further. I could also take, B to the n plus 1 and so on, but that will be the same. The geometric series terminates here, right? Because of these properties, you cannot, make any more progress as you add in higher powers. So this is the geometric series. So you can evaluate this. This is just the geometric series for the sum of the powers of B. So that's called B star. So that's a matrix. And as we saw in the first lecture this morning, so the entry in row I and j, row I and column j, is the length of a shortest path from node I to node j in G of B, but G of B is strongly connected. It's the same graph. G of B is the same directed graph as G of A, except the edge weights, are shifted by lambda. Okay, so that's the entry in row I and column j is the length of the shortest path from Busan to Rio de Janeiro. Okay. So now we're going to make an eigenvector as follows. I'm going to erase this, so you all wrote this down. You're ready to read it. As I always tell my students at Berkeley, if you want to come to lecture K, you have to read the material for lecture K after lecture K minus 1. Right? So you come to lecture K, let's say you want to, come to lecture 6 on Grassmannians. That means, before lecture 6 you read about Grassmannians. Okay, so and beer and pizza help to do that. Okay, so that's the cycle length. So let's continue the proof here. So let J be any node on a zero-length cycle. In this graph. So, this graph has some cycle of length 0. So let's pick a node and let x equals b star dot j be the corresponding column. Be the jth column of b star. Okay? So I pick a node j that lies on some zero-length cycle, and I take the corresponding column, the jth column, of the matrix B star, and then I claim that that's an eigenvector. Well, the first thing we note that xj, the jth coordinate, which is, B star jj, that's 0, right? So J is a city that lies on a zero-length cycle. But BJJ is the length of a shortest cycle from J to itself. But every cycle is non-negative. J lies on a cycle of length 0, so therefore the shortest length of a cycle, so BJJ star is 0. And that characterizes, those J. So we're interested in those J that have a 0 on the corresponding diagonal entry. Okay, that takes xj. So now we check, right? So now I claim that x is equal to the identity plus b times x. Why is that? So first of all, what's the identity? So the identity matrix, right, is infinity, infinity, infinity on the diagonal, and zeros otherwise. So this is the n by n identity matrix. So the tropical identity matrix has plus infinity on the diagonal, and it has 0 anywhere else. Now why does this hold? Well, the identity times x is x, and b times x. Well, what's x? Well, b times x is a column of b to the n plus 1. But b, well, that's because, right, so because x is a column, so note, the identity plus b times b star is equal to b star, right? So it's a geometric series, right? So the identity plus b times b star is equal to b. So therefore, that's true for every column, right? So therefore, x satisfies this equation, but that's equal to x plus b times x, and I claim that that's equal to bx, because in every coordinate, now I'm a little lost, one should never give proofs, right? So help me out. So I claim that in every coordinate, this is less or equal to that, and that follows from this equation. So since xj is 0, then you can so xj is 0. So therefore, if you look at, say, the ith coordinate of this vector, right, you have that the entry here, by taking j in the sum, you're going to be at least, you're going to be smaller. So certainly, xj will be appearing, and you can only go small, right? So I'm saying is that this vector, because of this equation, this vector in every coordinate is less or equal to that, which says it's equal to that. Okay? So this one implies that one. Okay? So now we're done, right? So this says x is an eigenvector of b with eigenvalue 0, right? So what I've shown is that b times x is 0 times x, but that's the same, as a times x equals lambda of a times x. So x is an eigenvector of b, it's an eigenvector of a with eigenvector lambda, eigenvalue lambda of a. Okay? So that's the eigenvector. And I've proved the theorem. Okay, let me put on my computer science hat for just 2 minutes and tell you how you actually calculate the eigenvalue. Why would anybody want to calculate the eigenvalue? Well, there was a gentleman here earlier who's interested in coding theory. So in discrete event systems, people are very, very interested in computing these eigenvalues. So for instance, there was a model made of the train network in the Netherlands. So how should the Netherlands have a very, very dense train network? And these trains, they run around, right? But you want to find the optimal cycle time. You want to find the optimal time so to make connections between the different trains. And that's a tropical eigenvalue problem. So that's a classical, cyclical discrete event system, such as running the trains in the Netherlands is a typical application, for computing eigenvalues of matrices. So how do you do this fast? So let me say a few words about this. And then I'm going to go back to math and geometry, but just a few words about the complexity. So how to compute? So questions, how to compute the eigenvalue lambda of a matrix. So do we need to inspect? Do we need to inspect all cycles? So, one algorithm, of course, is you draw the graph, you look at every cycle in the graph, you calculate the normalized length, and you take the smallest, right? But that's a very bad algorithm. So suppose n is 100, right, or 1,000. There are many, 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 many cycles, or as the computer scientists would say, there are exponentially many cycles. But we would like to have a polynomial time algorithm. So we can calculate this in polynomial time as follows. So no, we don't need. A colleague of mine in Berkeley, Karp, 30 years ago, already gave an efficient algorithm. So efficient means polynomial time. So if A is a very, very big matrix, a 1,000 by 1,000 matrix, you can find its eigenvalue very fast. And here's what you do. So proposition, the eigenvalue, the unique eigenvalue of a matrix, of a given n by n matrix, A, Aij equals the optimal value gamma star of the following optimization problem. So this optimization problem is a linear program. It's an LP, a very, very nice linear program, namely maximize gamma subject to the constraints Aij plus Vj greater or equal gamma plus Vi for all I and j between 1 and n. So you write down this very simple system of linear inequalities, n squared linear inequalities, where the Aij are given numbers and the Vij's and gamma are unknowns. Right? So these are the decision variables, are gamma and V. Then you take this, and if Aij is plus infinity, you don't need it. So you only write down those where Aij is a real number. You write these down, then you solve the linear program, and then the gamma coordinate of the optimal solution, the gamma star, that will be the normalized cycle length. It's exactly the number you want. And this is a very, very, very special linear program. You know, if you've taken computer science type stuff, you know that linear programming can be solved in polynomial time using interior point methods, but you don't even need that here. This is actually such a special situation. This kind of linear program you can very rapidly solve even without interior point methods, and you can do this for very large matrices. Okay, so now I'm going to take off my computer science hat. I'm going to put my pure math hat back on again, but maybe this would be a good moment to pause for a question. So every matrix has exactly one eigenvalue, and we can compute this eigenvalue very fast. You need that the graph is strongly connected. Yeah, otherwise, so let's say, suppose, so why does that fail? Let's take the n by n matrix where every entry is plus infinity. That's, or maybe, maybe that's not good. Let's take the identity matrix, right? Take the identity matrix that has zeros on the diagonal and plus infinity. Every vector is, maybe that's not a good example. But you can make examples, of sort of disconnected graphs that have more than one eigenvalue.
Is there also different ways of calculating using some possibility ideas, using like a term that is a characteristic polynomial?
Oh yes, of course. You can also calculate the eigenvalue by forming the characteristic polynomial, and you will this afternoon. So on the homework, there's a 3 by 3 matrix, and I'm asking you to calculate the tropical determinant, the characteristic polynomial. Now what about the roots of the characteristic polynomial? What happened? The characteristic polynomial is a polynomial of degree n, right? How many roots does it have? It has n roots, right? 2, 4, and 5, for instance, right? Are they all eigenvalues? Aren't the roots of the characteristic polynomial the eigenvalues of the matrix? You tell me at 5 o'clock, okay? I'd like you to explain to me at 5 o'clock why it is that in this theorem there's only one eigenvalue, while the characteristic polynomial, according to the fundamental theorem of algebra, has n roots. That's a bit strange, no? Question. Vj here and Vi there. What are they? Oh, what's the meaning? Well, okay, that's a good question. They are not quite the eigenvectors. The eigenvectors will be, so the solution set to this is a polyhedron, a classical polyhedron, right? So this will be describing a classical polyhedron. This classical polyhedron contains the eigenspace, but is not equal to the eigenspace. It's a little bit tricky, so I will not answer this question. It's a good question, but will take us too far to talk about this. I want to come to the eigenspace. Okay?
Excuse me?
Yes?
Is there any relation between the eigenvalue, the unique eigenvalue, and the unnormalized minimal length? You said the theorem said that the unique eigenvalue is the minimal value of normalized one.
Yes.
But I want to find some unnormalized. But any relation between
I see. In this setting, you need to normalize the cycle length. Yeah, I don't think. Maybe there's a way. Maybe maybe there's a way of fixing the matrix so that you can get other cycle length. I don't see it right now. So in this theorem, we need the normalized length. But maybe you can modify the matrix and pass to a different matrix so that normalized for one is unnormalized to the other. But I don't see it right now. It's a good question. But I want to talk about the eigenspace. So how to so how to compute and draw the eigenspace. How to compute and draw the eigenspace. That's going to be the theme. In fact, drawing is very important. Just for high school students and quadratic curves, I find it very important that we learn to draw this week. So we're going to talk about tropical curves and maybe linear spaces, things like that. But I think it's very important that we learn how to draw these objects. So I'd like you to learn how to compute and to draw the unique eigenspace. So the eigenspace of a matrix is the set of all x in R to the n such that AX equals the unique eigenvalue times x. Okay? And the eigenspace of A is, of course, the same as the eigenspace of B. So it's the set of all x in R to the n such that x is an eigenvalue of B, an eigenvector of B with eigenvalue 0, right? Or another way, I'm solving, it's a fixed point. Yeah? So x is fixed by B. Bx equals x. How do you find, the fixed points of the operator B on Rn? Okay, I'm going to give you the answer. So answer. So the first thing we're going to do, we note that this eigenspace, so this is a subset. But certainly, it's fixed under scalar multiplication. So if I have a vector x that's an eigenvector, and I tropically multiply it by some number, I still get an eigenvector. So it's certainly fixed under tropical scalar multiplication, which is the same as classical scalar addition. Right? So if you have an eigenvector and you add classically the same constant in every coordinate, you still have an eigenvector. That's, if you take the Netherlands, for example, and you run every train in the Netherlands, 3 minutes later, then whatever solution you had before, you still have a solution. So, okay, so that's tropical. You multiply every eigenvector tropically by a constant, or you scalar add by a constant. So that's okay. Since that's the case, we can identify the eigenspace. We can identify it meaning the eigenspace, with its image in tropical projective space. Tropical projective space. And I will define tropical projective space. I'm going to denote it by Tpn-1. I'm going to take the following definition of tropical projective space. It's R to the n as a vector space, as a classical vector space, modulo the one-dimensional subspace spanned by 1, 1, 1, 1, 1. So that's going to be my working definition of tropical projective space. So it's R to the n modulo the line spanned by the all one vector. So in classical math, this would be an n minus one-dimensional vector space. It's not compact, okay? And that's why some people don't like this definition. You could compactify this, and we can talk about this, but for now, let's use this definition of tropical projective space. So let me say this again. So projective space you get from a vector space by identifying two vectors if they differ by scalar multiplication. That's what we've done. That's exactly that definition. Okay, so I say that two vectors here are the same vector, if they differ by a global constant, multiplicative constant, and then I get this definition of tropical projective space. Okay. So that's very important for the drawing parts. When we draw pictures, we don't draw in our Rn, but we draw it in one dimension lower. Here's the theorem. Okay, so we're going to use the method that was used in the existence part of the previous proof. So let B star 0 be the submatrix of B star, the submatrix of B star, given by the columns where the diagonal entry B star JJ is 0. Okay, that's what I do. So I calculate the matrix B star and I look at the diagonal. At least one of the diagonal entries will be 0. Why is that? Well, because the shortest cycle length is 0 in B. So there exists some city, maybe Nagoya, right, that has a cycle of length 0. So that's I take the Nagoya column. And maybe from Nagoya I go to Sapporo and back to Seoul, then they're also, right? everybody who lies on some zero cycle in the network gets picked up. So this is a n by something submatrix. I'm erasing all those columns that don't have a 0 on the diagonal, and I keep those that do have a 0 on the diagonal. So then the theorem says that the eigenspace of A, which is the same as the eigenspace of B, is equal to the image of this matrix. Okay? And by image, I simply mean as a linear operator. So this is the set of all tropical linear combinations of the columns of B star 0. Okay? So that's the description of the eigenspace. The eigenspace, I've given you a generating set. Namely, I've written the eigenspace as the image of a n by something matrix as a subset of R to the n. And we're going to learn this afternoon how to draw the image of a matrix. Okay, let me sketch the proof. Is the statement clear? Right, so I claim the eigenspace. I calculate the eigenspace as follows. I have my matrix A. I calculate the eigenvalue. I tropically, I subtract it. I get B. I form B star. Then I keep those columns that have a 0. That's B star 0. And then I calculate and draw the image of that matrix. And that's precisely the eigenspace. Let me sketch the proof. So again, there are two parts. So I have to show. So this is what I have to show. And I'm going to show, this inclusion and then this inclusion. First of all, I claim that every vector in this image is an eigenvector. That's the easy part. So the easy part is we saw already that every column vector x of B star 0 is an eigenvector. However, the eigenspace is closed under tropical linear combinations. Right? If x is an eigenvector and y is an eigenvector, then x plus y is an eigenvector, right? Because there's only one eigenvalue, right? So x plus y is also. So therefore, this eigenspace is closed under tropical linear combination. So every column of this matrix is in the eigenspace. So therefore, the image of this matrix will be a subset of the eigenspace. Okay? So since the eigenspace is a tropical semi-module, it's closed under addition and multiplication, vector addition and tropical scalar multiplication. This one is contained here. So that's the easy part. So let me sketch the harder part. Okay? So the harder part is the converse. So suppose Z is an eigenvector. So it's an eigenvector of A or of B. So I need to represent Z as an image. I have to write Z as a linear combination of the columns of B star 0. Okay? And here's how I do it. Well, first of all, I observe that B star Z is also Z. So Z is an eigenvector of B. It's also an eigenvector of B star. Right? And that's B squared. So if I have an eigenvector, so if Z is an eigenvector of B, then it's also an eigenvector of B squared. Then it's also an eigenvector of B cubed. They all have the same eigenvalue, 0. Right? All of these powers of B have the unique eigenvalue 0. So therefore, it's an eigenvector of B star. Right? So that's clear. So B star Z is equal to Z. So let Z tilde be obtained from Z by erasing all coordinates j with bjj positive. So these are the irrelevant coordinates. So I take z, so z is a column vector, but I'm erasing all those coordinates that come from a city, maybe Beijing, that doesn't lie on a zero-length cycle. And then I take a shorter vector. So z twiddle is a restriction of to all those cities that do lie on a zero-length cycle. So that's z star. So I claim that b star 0 times z tilde is equal to z. Okay? And that will complete the proof. And this would take me about 10 minutes. Now I only have 7 minutes left. I do plan to go over time by 1 minute. So maybe I have 8 minutes. But that's still less than 10. So I'm not going to go through the proof. So there's a proof. You check this again. It's one of those cycle arguments. You go along a cycle. By another one of those cycle arguments, you can show that b star 0 times z tilde is z. So therefore, z is in the image. Okay, so take any z here. It's in the image over there. And besides, the proof is in the notes. So this manuscript I have with Diane McLagan is terrible. It's incomplete. There are mistakes. And it's very preliminary. But this part is written up carefully. So this part you can. Okay, so I'm not going to do the proof. So that completes that proof. Instead, I like to draw a picture for you. Okay, so now you know how to calculate the eigenvalue and the eigenspace. And I like to argue that the eigenspace is actually a very interesting object. It is not, as we shall see, a tropical linear space. It's a tropical polytope. It's actually an eigenpolytope. Okay? So let me explain that in an example. Let's do a very simple example. And draw the eigenspace in the plane. TP2, right? So the tropical projective plane. So I'm going to do this for you now. Okay, so let's calculate, the eigenspace, and let's draw it in the plane. Now, first of all, how should we remember what is the tropical projective plane? It's really, R3 mod the all 1 vector, right? So people who study representation theory call that the root lattice of AN, right? Really, that's what it is, or the apartment of the affine building. So we can use fancy math names, but we're still at the undergraduate level. So this is just the R3 modulo the all 1 line, and we can draw in it. And the way we're going to draw in it, we're going to use, we're going to normalize so that the last coordinate is 0. So in this projective space, when I draw a point, I'm going to use homogeneous coordinates x, y, 0. So the last coordinate is always 0. Remember, 0 is the multiplicatively neutral element. Right? So if I have a point, 2, 5, 3, and I say draw it in the plane, right? That's the same. And I multiply by -3, so I get -1, 2, 0. So I draw it as -1, 2. Okay, so that's how I'm going to draw points in the plane. So let's do it. It's a convention, right? So my convention for tropical projective space is that I normalize the last coordinate to always have the multiplicatively neutral element 0 in the last coordinate. Okay, well, so in this case, it's very, very easy. So let's calculate. So in this case, lambda of A is 0, right? On this airline, staying anywhere, costs nothing, and going from any city to any other city costs 1, right? So therefore, the shortest normalized cycle length is just staying at any city, so that's 0, right? The self loops have length 0, so therefore lambda of A is 0, A is equal to B, and B is equal to B star. So I've picked a very simple example, in general, such as, in exercise 5 this afternoon, you will actually have to do something. You have to actually calculate, lambda of A, and then you have to calculate B, and then you have to calculate B star. But in this case, there's nothing to calculate. Now, also, B star in this example is equal to B star 0, right? Because this is B star, so now we look at every column that has a 0 on the diagonal, so that's already equal to B star. So I picked a very, very simple example because we only have 1 minute plus regular time plus 1 minute overtime. We will not do any penalty kicks. Okay, so that's 2 more minutes. Okay, so let's draw it. Okay, well, let's draw the plane. So here's the projective plane. So maybe here's the point, 0, 0. So this is 0, 0, 0. So then let's draw the columns, right? So let's draw these points. This point, this point. Let's draw this one first. So 1, 1, 0 is this point. So this is the point, 1, 1, 0. Then this point is the same as 0, minus 1, 0. So that's 0, that's here, right? So that's 0, minus 1, 0. And the first column is minus 1, 0. That's here. Okay, that's this one. So that's the first column, second column, third column. Okay. And now, you can take linear combinations. So for instance, maybe we could add these two. Okay, if we add these two, then we get 1, 0, 0. Right? So if I add the first and the last, what? I get 1, 0, 0. Oh, the last two, I get this one, right? So this plus this is that. And then, I also get these. And you do this for a while, and you get this hexagon. So this is an example of a tropical triangle. So the image of this matrix, the linear combinations of this vector, and this vector, they form this tropical triangle with this vertex, and this vertex. You can do this, and so we'll see some other examples. So by a tropical triangle, I will mean the image of a 3 by 3 matrix. Just calculating the image. Okay, so that's the end of the second lecture. So if you're interested in doing some of these problems, so see you at 1:30 or let's say 13:30 here.